Welcome back to our last section for 9.4. And for this one, we're actually going to look at how we can kind of connect together our thermodynamics with the kinetics. So putting the pieces to the puzzle together for why a reaction might proceed to equilibrium or why it might take a long time to do so. Okay, so we're getting into the concept known as kinetic control. And we might have a reaction that is considered to be thermodynamically favorable, but we don't actually see it doing anything, right? It doesn't make products at a measurable rate. It is not proceeding towards equilibrium very quickly. And basically what all that means is that if we have a reaction like that, it has a large activation energy. Okay, so it's EA, that peak in our energy diagram is very high. Okay, so if it has a large activation energy, even if it's thermodynamically favorable, it's going to proceed very slowly. Okay, it's a process that's not at equilibrium, it's very slow, and it would be said to be under kinetic control. Okay, so now what's important, especially in biological systems, catalysts help to lower the activation energy of a process. So that's really important in our bodies. It's also really important for a lot of industrial reactions that are necessary for producing certain things. So catalysts play a major role in chemical reactions that are important for us as humans. So what they would help us to do by lowering the activation energy, that peak that we would normally have to get to with the reaction under normal conditions, with the catalyst, that actually lowers our peak. So now we don't have to provide as much energy to get to our, get up to the peak of our activation energy. Okay, so a catalyst, as a result, increases the rate of the reaction, but it does not affect the process's thermodynamic favorability. We still have the same reactants, we still have the same products, okay? So delta H, delta G, delta S, they're unaffected by this, okay, adding a catalyst. But what it does do is it shortens this peak, okay, where it's more attainable at whatever temperature we're at. Okay, so now let's get into a couple of questions. So the reaction shown below occurs at 200 degrees Celsius. Why does it only occur at a significant rate above this temperature? Okay, so we've got lithium nitride and hydrogen reacting to form LiNH2 and LiH. Okay, so the delta H of the reaction is negative 192 kilojoules per mole. So the change of enthalpy is negative. And that's usually a good sign for a thermodynamically favorable reaction. But if we take a look here, we are likely going down in entropy, right? So solid and a gas making two solids, right? So that's something to consider. So why is it only going to happen at a temperature above 200 degrees Celsius? Well, the main reason for that is because it has a high activation energy. Okay. Let's look at another question. All right, so looking at these diagrams over here, we've got the same reaction, but check out the peaks, they're different. So the combustion of C2H5OH is represented by the equation above, and the standard entropy and enthalpy changes of the reaction are provided. When the reactants are combined at 25 degrees Celsius, essentially no carbon dioxide, no water is produced after a few hours. Which of the diagrams to the right would best help to explain the low yield of a reaction under these conditions and why? Well, the main reason, look at that activation energy. Diagram 2 has that higher activation energy, so that would explain why, even though we have an exothermic reaction, we have to get to the peak here, we have to expend enough energy to get up there, and without that, we're not making it up there to then go and produce those products. okay? So the answer for this is C, diagram 2, because it represents a reaction with a high activation energy barrier for molecules to overcome and a very slow reaction rate, even if it is thermodynamically favorable with delta G being less than 0, okay? So yeah, I mean, we have a positive entropy, we have a negative enthalpy, and in those conditions, it should always be thermodynamically favorable, right? But the problem is getting to that activation energy. All right, and then for number 3, check out this reaction. So diamond forming graphite has a delta G of negative 2.9 kilojoules per mole. That should tell us that it is thermodynamically favorable, right? So which of the following best explains why the reaction represented below is not observed to occur at room temperature? That'd be cool, wouldn't it? Being able to convert diamond into graphite, I guess, if you want to do that, you know, turn diamonds into pencil stuff, but you know, whatever. So the answer for this, again, is actually going to be C. So being able to convert diamond into graphite while being thermodynamically favorable, it does not happen as a result of a very high activation energy. And that's due to the 3-dimensional bonding between carbons in the diamond, okay? And that's all for this section as well. So basically what you should get out of this, if we're looking at a thermodynamically favorable reaction that isn't doing anything, the reason why is going to be mainly because of a high activation energy. All right, and that's all for this section. And the end of this module. So all you need to do now that you've watched all these videos is answer the questions in the Google form that you have available